All right, let's get right into it. Today, we are not doing a coding tutorial. Think of this as a strategic briefing for leaders. We're going to crack open the black box of large language models and figure out exactly how you can build incredible, proprietary AI without burning through your entire runway. Okay, let's dive in. This right here, this is the core of everything we're talking about today. The difference between winning and losing in AI right now isn't just about who has the best idea, it's about who has the most efficient architecture. The cost difference is, and I mean this literally, staggering. And it's what separates the startups that make it from the ones that don't. So where is all this money actually going? Well, a really important study from Microsoft looking at their own internal systems found something pretty shocking. Most of the time, these big, expensive deep learning jobs were using half or even less of the GPU power they were paying for. This isn't just a small leak, it's a fire hose of wasted cash. We're basically paying for a garage full of Ferraris and only ever driving them in first gear. We have to fix that. Okay, so to figure out how to save the money, we first have to understand how the machine actually works. So for this first part, we're going inside the LLM factory to really demystify the core parts. And don't worry, forget the complex math for a minute. We're going to use a much simpler analogy. You know, the heart of every single modern LLM, from Llama 3 to GPT-4, is something called the Transformer architecture. The easiest way to think about it is to imagine a giant corporate meeting. Every single word you type into your prompt, that's an employee or a token walking into the meeting room. Their job is to figure out what this meeting is all about. So what's the very first thing that happens when all these employees get in the room? A process called self-attention. It's exactly what it sounds like. Every employee, every token, looks at every other employee in the room to figure out who's important and what the context is. You know, if the word bank walks in and sees the word river, it instantly knows, I'm a river bank, not a financial bank. It's this huge parallel conversation where every word gives meaning to every other word. And boom, here it is, our first massive economic problem. This whole attention process, it's quadratically complex. What that means is if you double the number of employees in the meeting, in other words, you double your prompt length, you don't double the cost. You quadruple the number of conversations that have to happen. This is exactly why super long context windows get so unbelievably expensive. The cost doesn't just go up, it explodes. So, where does the model's intelligence actually come from? It comes from its weights and biases. Just think of them as the model's brain cells. The weights are basically the strength of the connections. That's all the knowledge it's learned. And the biases? They're kind of like a neuron's preconceived opinion or a gut feeling on whether it should fire or not. So when you hear parameter count, just think number of brain cells. So what does a huge parameter count, like 70 billion, mean in the real world? It means that a model like Llama, in full 32-bit precision, needs 280 gigabytes of VRAM. And that's not to run a query, that's just to load it into memory, just to wake it up. That immediately puts you on a super expensive server-grade GPU like an NVIDIA A100, which can cost you dollars per hour. This is the big hardware problem we have to solve first. All right, so if the brain is too big to fit on any hardware we can actually afford, the next logical step is pretty simple, right? We've got to shrink it. This section is all about the magic of optimization, and we're going to start with a technique called quantization. Quantization, at its core, is just a fancy word for compression. We're taking all those weights in the model, which are stored as these really high-precision 32-bit numbers, and we're crunching them down, usually to 4-bit. I love this analogy. It's like taking a beautiful 4K high-def movie and compressing it down into a GIF. Yeah, you lose a tiny bit of detail, but the file size just plummets. And this just shows you exactly what's happening. A full precision weight is this long, super detailed number. The quantized version? It's just a simple integer. We're essentially just rounding things off. But when you do that across billions and billions of parameters, the total savings on file size is insane. It's an 8x reduction, going from 32-bit to 4-bit. And the results of all that compression? Well, that 280 gigabyte monster model now only takes up about 40 gigs of VRAM. All of a sudden, you're not locked into that expensive A100 anymore. This model can now run on a high-end consumer graphics card, like an RTX 4090, or even inside a free Google Colab notebook. The cost savings are instant, and they are massive. Okay, so we've shrunk the model down so it can actually fit on our hardware. Great, but now, how do we teach it new things without going broke all over again? Well, that brings us to our next section, where we're going to focus on this incredible technique called low-rank adaptation, or just LoRA. So the old way to do this was called full fine-tuning, where you try to adjust all 70 billion weights. It's crazy slow and expensive. LoRA is so much smarter. What you do is you freeze the entire pre-trained model. All those billions of brain cells are now read-only, and you just attach this tiny new layer of trainable weights on top. It's like putting a small editable sticker onto a giant printed textbook. And here is the economic punchline. With LoRA, you're only training a tiny, tiny fraction of the total model, like 1 or 2% of the parameters. The business analogy is just perfect. Instead of spending 6 months and a ton of money to re-educate a senior employee from scratch, you're just handing them a new one-page checklist for a very specific task. It's way faster, way cheaper, and it's surgically precise. Okay, so we have the theory, we've got a quantized model, and we're going to use a LoRA adapter. But how do we actually put those two things together in the most efficient way possible? This section is about the tools that combine these ideas into a real cost-cutting weapon. And the hero of this part of the story is a library called Unsloth. What Unsloth does is, it's just genius. It goes deep under the hood of PyTorch, the standard tool we all use, and it manually rewrites the core code, the kernels, to be hyper-optimized for exactly this kind of LoRA training. And the results are just wild. Your training runs are twice as fast, and they use 70% less memory. You know what the best part is? It makes the whole process incredibly simple. This is it. This is the whole workflow. You load your model in 4-bit, you attach your LoRA adapters, and then you just train it. Unsloth is doing all the heavy lifting and the crazy optimizations in the background. It hides all the complexity and just gives you pure performance. And this right here is the ultimate payoff. When you combine quantization with LoRA, with the Unsloth engine, fine-tuning goes from being this big, expensive thing you need multiple GPUs for, to something you can literally do for free. You can fine-tune one of the world's best open-source models on the free GPU that Google Colab gives you. It's a total game changer. It completely democratizes AI development. So, you've kicked off your training run, everything's going, but this leads to that one nagging, anxiety-inducing question that every single one of us has. Is it actually working? Or am I just lighting a pile of money on fire, burning GPU hours on a model that's going absolutely nowhere? How do you know? And that is where a tool like Weights and Biases comes in. It's basically your mission-controlled dashboard from model training. It tracks this super important number called loss, which is just a measure of the model's error rate. And it's simple. As the model trains, you want to see that loss curve go down. If the line is going down, it's learning. If it flattens out, or even worse, starts going up, something's wrong, and you can kill the job right then and there before you waste another dime. All right, we've gone through the theory, we've covered the optimization tricks, and we've seen the execution stack. Now it's time for the final and, frankly, the most important part. What does all this mean for your bottom line? Let's put all the pieces together. Let's just break down these numbers because really, this slide tells the entire story. On the far left, you've got full fine-tuning a 70 billion parameter model. Look at that. You need 600 gigs of VRAM. That's a whole cluster of GPUs costing maybe $20 an hour running for 20 hours straight. Now, look at the far right, the Unsloth quantized LoRA approach. Your VRAM requirement drops to under 50 gigs. Your hardware cost is less than $1 an hour, and the time, 4 hours. This is not a small improvement. It is a complete paradigm shift in what's possible. And this is the one thought I really want to leave you with. Choosing this modern stack, quantization, LoRA, and an optimized engine like Unsloth, it's not just a technical choice. It's a financial strategy. It is how you build custom, powerful, proprietary AI models on a startup budget. This isn't just code. It's a competitive advantage that can save you over 95% of your budget.